Hello, students. So, continuing our lectures on electronics and especially the tunnel junctions formed by means of quantum dots between two leads. We have previously derived these equations where the voltage at the two terminals can be A and B can be represented in terms of the source voltage, that is the CS source or the source capacitance. You can find the lectures in this. You can find the details in this lecture. Now, the voltage drop due to an electron tunneling through. These are the two leads, and there is and quantum dot in between. There will be a voltage drop at these two positions, which we have marked as A and B. Now, if the voltage drop in these two positions can be represented again after electron has tunneled by the following relationship. That means we are just adding up one electron with the previous existing electron here or the charge here. So these two add up and they give you the final voltage drop after the electron tunneling has taken place. Now, since the total source voltage will be always equal to the sum of the voltages at the two, or the sum of the two drop voltages, the same we can say about the charge, since the charge contained in the side A is again related to the voltage, and so we can equate this and we get for equation that the final charge content is related to the initial charge content, and the difference is caused by this amount. Now, we must understand that whenever there is an electron tunneling take place through the island, uh, the charge supplied by the voltage source is not simply the one that tunnels out. The charge, the change must also come from the power supply, and there is a supply work associated with this to transfer the electron. Now, as the electron transfers takes place, if we calculate, then the voltage dimension or the value of the voltage again comes out to be equal to that of the electron tunneling, that is E by 2C as the Coulomb voltage and E square by 2C as the other voltages. Now, uh, let's now look into this energy band diagram of the system. Now we'll start with the very basic system. If the system is large enough and also the capacitance at the two junctions are equal, so in that case the charge on the island will not get discretized. There won't be any energy levels formed, and that is showing that the island and the lead are of the same material at the thermal order. In the other thermal order, there won't be any energy levels, any discretization of energy possible. There won't be any energy levels formed here. Now, if we go to the second case, in this case, if we are supplying a voltage V0, then the electron transfer actually starts to take place from the Fermi energy level of, say, this is say B or A, from this part to the other part. Electron transfer starts to take place. Voltage, bias voltage is being applied. Now, the island is again if very small, then the energy levels will be discretized. As you can see here, energy levels have been discretized, and the difference between these two, the energy gap existing, is E square by 2C. No. Now this change in energy square to C is. हाँ बोलो. हाँ 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 क्लास में गया. 3 बजे है ना? Okay. So, so when the island is very small, the energy level is getting discret- discretized, and there is an energy gap existing where there are no states formed. Now, these energy levels are above, symmetrically placed above the Fermi level, as can be seen. Now, at this point of time, when the size is also small, and there has been a certain amount of discretization taking place, we apply a voltage. We apply a voltage which is more than the bound voltage or the energy or the bound energy level. Now, in this case, what happens is that already there are certain energy levels existing, and if you are again supplying, there's a tunneling of a second electron. It is already uh, discretized states. What happens is that there is an adjustment taking place, that the energy bands they adjust among themselves, and there is also a Coulomb blockade existing, but the Coulomb blockade now it goes to a higher level. That means from E by 2C, the E by 2C, the Coulomb bracket now is 3E by 2C. Is 3 by 2C. As you can see, if there is already existing discretized situation, there is a tunneling of current take place. The the source voltage again is equal to E by 2C. That means the voltage which is causing the transmission to take place. This is also equal to E by 2C. So we can have a general formula because there will be a tunneling of electron one by one. So for the first electron tunneling current, it's E by 2C. For the second, it's 3 by 2C. So what we observe that for the general formula is Vs plus M plus 1 by 2C. So there are 3 electrons being tunneled. So it will be 4 E by C, so on and so forth. So these discretized steps actually they form the Coulomb staircase, which is again previously we have explained it. The voltage value is E by 2C, and the current value is when we are dividing the electronic charge by tunnel junction and capacitance. Now we can also have a situation where we have an asymmetrical junction. By asymmetrical junction, we mean that the distance between the dot and the two leads are not uniform, may not be equal. So the one which has got higher gap, like in this case, this A junction, the resistance at this point will be higher than the one which has got a lower gap. And what this system does is that as soon as there is a transfer of electron taking place, the junction is this. So this there is a quick replacement taking place. So this one gets quickly replaced. Okay, so there won't be a situation where there will be any empty states. So the junction is approximately current. This results in approximate current. Now, what we have found is that we require a very low temperature and very small value of capacitance to observe a Coulomb blockade. And on the other hand, a very large resistance is required. And if R is smaller of the two symmetric, okay, so we can write it in this fashion: R tunnel resistance is equal to more than 1.2 ohms. Okay, now this is a situation where if we consider a metals and semiconductors, the difference between metal and semiconductor in terms of Fermi level is that the metals have highly energized Fermi levels, since there is its conduction band is partially filled. So due to that, the energy levels are very closely spaced. Even if the discretization is taking place, the energy levels are very so closely spaced that the electron may leak out from one energy level to another energy level. So this is called actually a quantum quasi-quantum state. The quasi-quantum state is that the boundness of the electron and a potential well or an energy level is for a finite amount of time. So this gives you quasi-quantum states, and these quantum states again can be represented by the energy can be represented by easy E is equal to E0 minus I E0 minus I gamma. Now, practically, this tunneling can be visualized by a process called scanning tunneling microscope, where you have an aluminum substrate above which there is an oxide layer, which is about 1 nanometer height or thickness, and so this forms a metal semiconductor and a metal junction. Now, if there is an electron tunneling taking place through it, so that gets detected by this STM tip, which is also based upon and tunneling. So the first tunneling influences the second tunneling, and we get a tunneling current. The IV plot of this tunneling, if you look carefully, what can we observe is that this Coulomb blockage value, which is around which is V by 2C, is 22 millivolts. So, by using calculations, what we have found is that this capacitance turns out to be in the antifarad range, and the current observed is in nanoampere range. Why the Fermi level in the case of electrons is more the wavelength of the Fermi wavelength of the electron is more simply because of the fact that the electrons are not, or the semiconductors, they have a gap in between the conduction band and the valence band, and so this energy level is zero, so naturally their wavelength will be zero. So it's therefore it is say that the quantum dot, making a quantum dot of a silicon, is much higher than that of any semiconductor.